So modern data can be massive and messy. It's often called big data, and our first goal is to understand what it is and how to work with it. So what is big data? Well, big data refers to data sets that are both large and very complex. Complexity is a mathematical term, which is high variety, and it means the data has a complicated underlying structure. We'll start using the word topology in this context. For example, a document is a word structure, not just a set of words. Curves are point structures, not just sets of points. That is, structure is as important as size. So big data is often described by the 3 V's from Gartner Incorporated. Big data has high volume, massive is high velocity, uses algorithms, and high variety, it's messy, requiring new forms of processing to enable enhanced decision making, insight discovery, and process optimization. And we always want data to have high veracity, be reliable and high quality, low noise, unbiased, so on and so forth. But even big data can be bad data. For example, if we look at this problem of x to the fourth plus 4, it can be factored. I show you the factorization. But if I ask ChatGPT to factor, then it uses a difference of 2 squares. That's incorrect. It's a common high school mistake. And huge amounts of ChatGPT training data is from an internet full of common high school mistakes. So high veracity is non-trivial, but it's also an issue more appropriate to a different course, for example, one in experimental design. So we're going to be looking at the 3 V's: high volume, high velocity, high variety. For example, large language models require huge volumes of documents, websites, Wikipedia, novels. But you can't build a large language model solely from dictionaries. Why? Dictionaries don't tell a large language model how to form sentences and paragraphs. It's just sets of words. In some sense, a dictionary is all the words. But the information in a document is a structure built from those words, not the fact that those are all the words. Even seemingly ordinary data, rectangular arrays, can occur in a surprisingly high variety of ways. So here's what rectangular arrays are. Rows of observations, columns of features, M observations, N features. This is an M by N array, denoted R to the M cross N. That's a set of all possible M by N arrays. And the high volume is typically because M is very, very large. So let's look at the high variety of ways that data can occur, even though all these examples are just going to be rectangular arrays of numbers. For example, we might have a data set, features and observations. Here we have calculus students take 4 exams and a final, each out of 100 points, and some other features. So previous is 1 if the student had calculus earlier, high school or repeating the course, and 0 otherwise. Textbook is 1 if the student had the textbook during the course. Time of day is the time of day the course is taken. GPA is a student's grade point average. Average minutes is the average amount of time a student spends on an exam. Now, this actually is not actual data. It's generated from an original data set, and that generating the data anonymizes the original data. So movie streaming. Viewers rate movies they stream. Ratings often 1 to 5. 0 means the movie is not rated. Well, this is again a rectangular array. Each viewer, however, rates only a small percentage of all the movies available. So most of the ratings are zeros. An array which is mostly zeros is said to be sparse. So it's a rectangle, but unlike the previous data set, this is a sparse data set. What about word counts in plays of Shakespeare? So here we have, for example, Anthony occurs 73 times in the play Julius Caesar. This is again a sparse matrix. Only a small percentage of the coefficients are non-zero. What about a grayscale image? Well, now we have a rectangle, but we don't have features and observations. This actually should be considered simply a rectangle, an m by n rectangular array of numbers. It's a dense matrix. Most of the coefficients are not zero because most of the pixels are not black. So even though superficially all of these have been rectangular arrays, they all have different structures. Graphs and networks. You describe them using an incidence matrix. For example, if we add an edge E7, then we add a row to model the connectivity of E7, that edge. For large networks, each row is mostly zeros. In fact, there are in each row only 2 non-zero entries. Well, what about time series? Time series, well, this is once again a rectangular array, but it's not sparse, and it's a different form of data, even though everything we're looking at. So here's another way of looking at observations of features. You could think of having variables that are sampled to form an m by n array. So if I had, for example, exam 1, exam 2, exam 3, exam 4 as variables, then all of these numbers could be thought of as samples of these variables. So a feature can be considered a variable which is sampled to produce data. Now, if you do that, then the variable has an average over those samples. So the class average for exam 1, the class average for exam 2, and we have to be careful now because we're going to get some important terminology. This is what's known as an empirical mean because it's an average over the data itself. An expected value is a limit of empirical means as the size of the samples goes to infinity. Sometimes we use mu notation. Variance is the expected difference of the squares of the samples with the data, the expected squared error. Now we're only going to work with features that have a finite expected value and a finite variance. But notice that both of those are limits, and what we're saying is these limits exist. So notation, R m cross n is the set of all m by n arrays. So the set of all m by n arrays is a vector space. And notice that the arrays in data science are seldom square. So if we have column arrays with m real coefficients, that's just Rm. And Rm is a method for writing, therefore, Rm cross 1, one single column. A row is a transpose of a column, and vice versa. So for example, we could look at this word counts of words in the plays of Shakespeare. These columns are actually vectors in Rm. So we'll review and introduce concepts in linear algebra as we need, but I do assume that you know the following at this point. The dot product, which is very important. If I have, notice I've got U in bold equals U1 to UM transpose, so that means it's actually a column because the transpose of the row is the column. We often do this because that way we can write the column in line with the text by saying that you transpose it to make it a column. So we have U and V are in Rm. U dot V is the sum of the products of the coefficients respectively. Matrix multiplication. If A and B are matrices, then AB is an array of inner products of rows of A with columns of B. Real inner product properties. So the norm squared of a vector is the dot product with itself, and this cosine identity. And sigma notation. So the dot product, for example, can be written as a sum of the products of the coefficients respectively. So samples of features, we're very often going to think of as columns in Rm. So we're working with subsets of vector spaces. Now we may have several rectangular data sets. A box of rectangles, which we're often going to call a tensor. So for example, we might have a collection of spreadsheets. And this often is what leads to data sets being very large. If we have 100 spreadsheets with 100 observations of 100 factors, that's 1 million data points. Movie streaming, we saw this example earlier, but notice that we watch movies every day. So movie streaming data probably is best thought of as a box of rectangles. Millions of viewers times thousands of movies times thousands of days. That's trillions of data points. High volume, huge numbers of observations of high variety data structures with many variables. Structured data could be boxes of database tables. So, a lot of companies have databases housed in several different locations. Databases tend to contain many different tables. So we may want to think of those as a box of rectangles. On a box of rectangles, again, we're often going to call these tensors, especially when we work with images. For example, this color image is actually a box of 3 images, one corresponding to intensities of red, one to intensities of green, and one to intensities of blue. So this box of rectangles is a tensor. Video is a box of color images. So once again, it's going to be a tensor. So all tensors with the same dimensions forms a vector space. So for example, all color images of the same size forms the vector space R m cross n cross 3. Sometimes we call this a tensor space because it's a vector space of tensors. So tensors is linear algebra with multidimensional arrays, linear combinations, dot products, basis, span, so on and so forth. We're not going to need the separate field of tensor algebra or multilinear algebra, and we don't really need to generalize matrix techniques to tensors, because for us, our tensors are going to occur in vector spaces. In other words, tensors are going to be vectors that are in vector spaces called tensor spaces. And therefore, we can just use linear algebra, which is, of course, the study of vector spaces. So a set of data is structured if it can be represented by a subset of a vector space. Very important concept. We're going to be studying subsets of vector spaces. Unstructured data. Data may not be in the form of boxes of rectangles. For example, we might get these key value pairs, JSON type data. It's analogous to Python dictionaries. However, very often, unstructured JSON-style data can be translated into sparse tensors where most of the coefficients are 0. Not going to show you that here, but it does say that our focus on structured data, boxes of rectangles, tensors, which most of the time we're just going to be looking at matrices and two-dimensional rectangular arrays of data, that's really going to be our focus. So data science is the study of big data. Modern data that's a massive collection of computationally expensive, messy observations. High volume, high velocity, high variety. However, after we've done enough pre-processing at least, most of the time, and pretty much all the time in this course, the data is going to be in the form of tensors in a well-defined tensor space. And most of the time in here as familiar two-dimensional arrays from matrix algebra. That is, big data is modern data, and the purpose of modern data is to capture massive amounts of information. But modern data is not always big, and we'll often use only medium-sized data, structured data, subsets of vector spaces, because the goal of the course is to introduce the new skills and new models necessary for high variety data. In other words, in this course, we focus on high variety, which often requires high volume and high velocity. But high variety means the information in a set of big data has a complex shape. Soon we'll use the word topology. And the purpose of data science is to extract and study the content and character, i.e. topology, of the information in 3V satisfying large, complex modern datasets.